a brief introduction to George. He recently joined the staff of Aerospace Engineering in TU Delft after an international career, starting in Greece, continuing in Switzerland, United States, and now in the Netherlands. Especially, you can all read it, but you can see that already his PhD thesis was very well received, and it was already on the morphology and optical properties of flame-made nanoparticles. But the topic of today is very wide. It's trying to find the interesting connections between the good and the bad aspects. So, George, if you want to add anything to this introduction, you can, but we are especially looking forward to your presentation. So please go ahead.
Thank you so much, Dick, for the very nice introduction, and thank you very much for the invitation to present to the Dutch section of the Combustion Institute. Today I'm going to talk about combustion-generated carbonaceous nanoparticles. And of course, carbonaceous nanoparticles are typically viewed as a nuisance by combustion science and engineering, as soot is a byproduct of incomplete combustion of hydrocarbon fuels. In fact, 8 megatons of soot nanoparticles are emitted every year all over the world. You can see in this map over here the surface-based mass concentrations of soot emissions at different regions of the world. So in Europe and North America, most of soot emissions are coming from road and air transportation. While in East and South Asia, for example, soot nanoparticles are emitted by coal and biomass combustion. And of course, soot nanoparticles are being emitted by the forest wildfires that unfortunately they make it more and more often on the news nowadays. Now, soot nanoparticles contribute to global warming as they absorb strongly light. And in addition to their climate effects, they have also a detrimental impact on public health. In fact, a recent study from Harvard University was highlighted by New York Times as it showed that even small concentrations of soot nanoparticles can increase the mortality risk of elderly people by 6 to 8%. So in order to understand and mitigate and eliminate the climate and health effects of soot, we need to understand how soot is formed during combustion. And for simplicity, I'm going to show you this for a simple premixed ethylene flame that you can see in this image over here. Now, advanced experimental techniques have provided us insights even at the earliest stages of soot formation. For example, scanning tunneling microscopy have revealed incipient soot nanoparticles formed at very small residence times during combustion in this premixed ethylene flame. So these incipient soot nanoparticles are very small. They have a mobility diameter smaller than 3 nanometers. And they contain polyaromatic hydrocarbon molecules that are chemically bonded with each other. Now, as the residence time in the premixed flame increases, these nanoparticles react with acetylene as well as with other gaseous species in the flame, and they also start to coagulate and form small and compact nascent soot aggregates, as you can see in this helium ion microscopy over here. By aggregates, I'm referring to clusters of soot primary particles that are chemically bonded with each other. Now, as we further go up in the flame, and the residence time increases, the surface reactions gradually stop. So agglomeration of soot aggregates and agglomerates takes over, and we have the formation of large clusters of mature soot primary particles. So these clusters, they contain physically bonded soot aggregates and primary particles. And for this reason, we typically refer to them in the literature as agglomerates. These soot agglomerates are partially oxidized with oxygen and OH radicals at the exit of the flame, at the exhaust of the flame. So these reactions reduce the soot mass as well as its diameter, as you can see in this microscopy image. So you can see that even in this simple premixed ethylene flame, the morphology of soot changes drastically. as the residence time increases. So during my PhD studies at ETH Zurich, I developed a discrete element model to describe the morphology dynamics of soot nanoparticles during combustion. For the interest of time, I won't go through the details of this model. I just want to highlight that in this mesoscale discrete element model, we can follow in this simulation box in detail the particle motion and coagulation, either by coalescence or agglomeration. And in addition to this, we also account for surface growth by the hydrogen abstraction and carbon addition mechanism. So we estimate how many acetylene molecules react with the soot surface based on the respective reaction kinetics and collision dynamics. And then we increase the soot primary particle diameter by applying this mass balance over here for every acetylene molecule reaction. So of course, we wanted first to validate this model. So we compared it to the mobility size distribution data that have been obtained by a scanning mobility particle sizer as well as by microscopy in the premixed ethylene flame that I showed you before at the 1.2 centimeters height above the burner. In particular, over here, you can see on the y-axis the normalized number concentration obtained as a function of the mobility diameter. The mobility diameter is a diameter of an equivalent sphere that undergoes the same drag force with these soot aggregates and agglomerates that I showed you in my previous slides. The broken line over here indicates the median mobility diameter that has been measured by microscopy. So without discrete element model, we firstly made the common assumption that is made by many combustion models in the literature, even until nowadays. So we assumed that these very small soot primary particles behave like droplets. So as soon as they collide, they coalesce immediately to form a bigger sphere. These coalescence assumptions, though, as you can see, it results in an underestimation of the median mobility diameter by about 25%. Now, on the other extreme, we also estimated the evolution of the soot mobility size distribution by agglomeration alone, so in the absence of any surface growth. So you can see that this pure agglomeration model overestimates the median mobility diameter of soot by up to 4 times. So it's only when we account for both agglomeration and surface growth that we see the formation of these compact nascent soot aggregates that have a very similar morphology with those observed by helium ion microscope images that I showed you in my second slide. So the size distribution of these nascent soot aggregates is in excellent agreement with the mobility size distributions measured both by microscopy but also by a scanning mobility particle size. Now next we wanted to quantify this ramified morphology of soot aggregates and agglomerates. And typically, the common parameter that is used to quantify the agglomerate and aggregate structure of soot is the effective density. So over here on the y-axis, I'm presenting you the normalized effective density obtained as a function of the normalized mobility diameter. The mobility diameter is normalized, it's divided by the mean diameter of the primary particles that make up this agglomerate, while the effective density is normalized by the soot bulk density. So as you can see over here, the effective density of these agglomerates is only a small fraction of the soot bulk density. And here this line has been obtained by discrete element modeling simulations that have been done at various temperatures and various fuel concentrations. So you can see that our simulations, when we normalize the effective density and the mobility diameter, have a very small statistical variation that is quantified by this small error bar. So the effective density decreases as a function of the mobility diameter. So as the soot aggregates and agglomerates become larger and larger, they become more porous and their effective density decreases. And this reduction of the effective density can be described by this simple power law that we derived with our discrete element model. So we compared this power law to experimental data of the soot effective density obtained for soot from premixed flames as well as diffusion flames and even soot coming from real diesel engines. As you can see, this power law over here is in excellent agreement with all experimental data sets that I'm presenting you over here. So this good agreement indicates that the morphology of the simulated soot agglomerates that we obtained with this discrete element model is very realistic. So we used these simulated soot agglomerates and this power law over here to assist the monitoring of soot emissions using aerosol diagnostics. So in particular, we were interested in monitoring the soot volume fraction as a function of the height above the burner in the premixed ethylene flame conditions that I showed you before. So over here, these two data points are actually coming from measurements of the soot volume fraction that have been done by coupling an aerosol particle mass analyzer with a differential mobility analyzer. This is the most accurate way to measure the soot volume fraction, as it accounts inherently for the morphology of these soot nanoparticles. The issue with this technique is that actually it's very tedious and time consuming. So as you can see over here in this study, the soot volume fraction was obtained only at 2 single heights above the burner. So what is a more common method in this field is to measure the soot volume fraction using only experimental data from a differential mobility analyzer, so only the mobility size distribution data, and assuming spheres. In other words, they are neglecting completely the soot effective density and they are using the soot bulk density. They are assuming spheres. So this is, of course, an oversimplification that results in an overestimation of the measured soot volume fraction by a factor of 4. And this overestimation is very large, and it can actually explain, to some extent, the discrepancy between combustion models and data that are often observed in the literature. So in order to address this issue, we also obtained the soot volume fraction using the same mobility size distribution data from this differential mobility analyzer, but this time we used the effective density power law that we derived using our discrete element model. So you can see over here with a broken line, it's the average soot volume fraction that we obtained this way, while the shaded area indicates the statistical variability of this power law. So the soot volume fraction that we obtain using data from a differential mobility analyzer, but accounting for the realistic agglomerate structure of soot, is actually in excellent agreement with the soot volume fractions obtained by an aerosol particle mass analyzer. And this accurate soot volume fraction data can be used to assist combustion models to close the soot mass balance. Now, next, we wanted to use the realistic soot agglomerates that we derived using this discrete element model to derive accurately the direct climate impact of soot. The direct climate impact of soot is typically quantified using its direct radiative forcing, which quantifies how much energy is added in the atmosphere by the soot light absorption. And typically, global climate models are estimating the distribution of the soot direct radiative forcing, assuming spheres. You can see, for example, such a simulation in this global map over here. So let me walk you through this rather complex map. The dotted regions indicate changes of the direct radiative forcing that are not statistically significant. So in Europe and North America, the direct radiative forcing of soot ranges between 0 to 0.5 watts per square meter. But there are still hotspots, including China, India, the Arabian Peninsula, and Western Sub-Saharan Africa, where large mass concentrations of soot can induce very large radiative forcings that range between 2 and 4 watts per square meter. Of course, these hotspots are not really new. Actually, they have been revealed also by climate estimations that are based on satellite observations. However, you can see over here that based on these satellite observations, the soot direct radiative forcing should range at these hotspots between 3 and 5 watts per square meter. And such discrepancies between climate models and satellite observations increase the uncertainty that we have regarding the climate impact of soot. So here we actually run exactly the same global climate model, but this time we accounted for the realistic agglomerate structure of soot using simulated soot agglomerates from our discrete element model. So when we account for the agglomerate structure of soot, the direct radiative forcing increases globally by 25 to 50%. And especially at the hotspots that I mentioned earlier, the direct radiative forcing ranges now between 3 to 5 parts per square meter and explains nicely the estimates based on satellite observations. Now, these large radiative forcings are very important because they can increase the regional temperature at these hotspots by 0.75 to 1.25 degrees. Now, in addition to the direct climate impact of soot emissions, these nanoparticles can also contribute to global warming indirectly. And let's go, for example, into the case of aviation, where most of the radiative forcing that comes from aviation is actually contributed by the contrails that are formed behind the aircraft engines. These contrails contain large ice particles that nucleate on top of soot agglomerates that are emitted by combustion of jet fuel. So recent climate model studies have shown that a 90% reduction of soot emissions can halve the global mean radiative forcing that comes from aircraft contrails. Of course, this is a global mean, and the reduction actually changes at the different regions of the world. So again, let me walk you through this global map over here. The lined regions indicate this time statistical changes of the radiative forcing that are statistically significant. So you can see that the largest reduction of the radiative forcing induced by this reduction of soot emissions is found in Europe and North America. There, the radiative forcing is reduced up to half watt per square meter. And this is actually the largest climate impact of soot in these regions of the world. Now, in addition to the climate effects of aircraft soot emissions, these nanoparticles are also very dangerous, very toxic for people working at the airports, as well as for communities living nearby, as these nanoparticles have been linked to respiratory and cardiovascular diseases. So it's very important to improve the design of aircraft engines in order to eliminate soot emissions from the atmosphere and mitigate their climate and health effects. Now, many of the current aircraft engines use the so-called rich, quench, lean concept. So, for example, you can see a cross-section of such a rich, quench, lean combustor over here, and along with the temperature profile shown on the right-hand side and the soot volume fraction profile shown on the left-hand side. These combustors contain two zones. We have the rich zone, where jet fuel is combusted at rich conditions and soot is formed. And we have also a lean zone, where air is injected to oxidize these soot nanoparticles and eliminate them. However, many of these soot nanoparticles are actually surviving oxidation and they are still released in the atmosphere. And this can be attributed to inhomogeneities of the temperature and gaseous profiles in the lean zone of this combustor that result in these pockets that you can see over here that contain large concentrations of soot nanoparticles. So in order to assist the optimization of this aircraft engine design, we used a lab-scale flame reactor for the enclosed spray combustion of jet fuel. So this flame reactor emulates the rich, quench, lean concept of these more large-scale combustors. In particular, in the rich zone, we have a rich spray combustion of jet fuel, and the rich and the lean zone are separated by a torus ring that you can see in these photographs over here. So using this torus ring, we inject nitrogen that either contains oxygen or it is pure nitrogen, and these gases are injected through 12 jets. So this torus ring, as well as the lean zone of this enclosed spray combustor unit, have been optimized to ensure good mixing between gases and particles. And in fact, this enclosed spray combustor unit have been used before to produce hermetically coated functional inorganic nanomaterials. But here actually we used this flame reactor to produce aircraft-like soot nanoparticles. In particular, over here you can see the mobility size distribution that we measured for soot nanoparticles generated by enclosed spray combustion of jet fuel when we used an effective equivalence ratio of 1.25 in the rich zone of this combustion. the shaded area quantifies the experimental variability of our measurements. Now, as we increase the equivalence ratio in the rich zone of this combustor to up to 1.59, the soot nanoparticles grow by surface reactions and coagulation, and this shifts the mobility size distribution to larger sizes. Now, we compared the mobility size distributions that we measured using this lab-scale flame reactor to those measured for soot nanoparticles emitted from real aircraft engines operated at different thrust levels, ranging from 3 all the way to 100% of thrusts. So by controlling the equivalence ratio in the rich zone of our flame reactor, we can actually reproduce the mobility size distributions of soot emissions from real aircraft engines. And actually, we have managed to reproduce other physicochemical characteristics of aircraft soot emissions, including their composition as well as their morphology. If you are interested, we can discuss about this in the Q&A session of my presentation. But a big advantage of this flame reactor is actually its high throughput. And to explain better what I mean over here, I'm presenting you on the right-hand side the mass concentration that we obtained as a function of the median mobility diameter of soot nanoparticles that have been generated at different combustion conditions. And as a benchmark over here, I have included the mass concentrations that have been obtained for soot nanoparticles generated using a commercial mini-cast generator. This is essentially a diffusion propane flame, and this is the standard device that it is commonly used by many aerosol and combustion laboratories across the world. And here you can see the mass concentrations that we obtained using our flame reactor for enclosed spray combustion of jet fuel. Of course, as expected, the soot mass concentration increases with increasing equivalence ratio and, of course, with increasing mobility diameter. But as you can see, the mass concentrations that we obtain using this flame reactor are up to 3 orders of magnitude larger than those obtained by the current commercial soot generator standard. So we took advantage of these large mass concentrations and we were able to collect large samples of soot at various equivalence ratios, as you can see in these images over here. So together with my colleagues at the School of Public Health of Rutgers University, we used the soot nanoparticles collected this way to characterize the inhaled dose of such aircraft-like soot nanoparticles and also to perform a toxicological characterization in order to quantify more accurately their impact on public health. Furthermore, using this flame reactor, we investigated the oxidation dynamics of soot in the lean zone of aircraft combustors. In particular, over here in this plot on the right-hand side, I'm presenting you the number concentration of soot nanoparticles measured as a function of the oxygen concentration in the injected nitrogen gas. So the number concentration is normalized here with respect to that we measured when we injected only nitrogen in the lean zone of this combustor. So when we inject nitrogen containing just 5% of oxygen, you can see that the number concentration hardly changes. But as we further increase the oxygen concentration, the number concentration decreases up to about 87%. Similarly, on the y-axis at the left-hand side of this plot, I'm presenting you the normalized soot volume fraction. So again, when we inject just 5% of oxygen, you can see that the soot volume fraction actually increases by about 40%. But as we further increase the oxygen concentration in the injected nitrogen gas, actually the soot volume fraction decreases up to 98%. So these large reductions that we attained by a judicious air injection in the lean zone of this flame reactor are very important because such large reductions of the soot number concentration and soot volume fraction can actually halve the climate impact of contrails that are formed behind the aircrafts. So this flame reactor can be used to investigate the oxidation dynamics of soot nanoparticles in the lean zone of aircraft combustors. And that way, we can assist the elimination of the soot climate and health effects. Of course, again, up to now, I have talked about carbonaceous nanoparticles as a nuisance. But even though Soot is a nuisance for combustion science and engineering, these nanoparticles are actually a blessing for material science. For example, carbon black is the largest nanostructured material that is produced industrially today, both by volume but also by value. Carbon black was firstly produced back in ancient China. So back then, these Chinese workers would use the lamp black process to produce carbon black nanoparticles and make their famous inks. Nowadays, the lamp black process has been replaced largely by the furnace process to produce 11 megatons of carbon black every year. So in this process, we have essentially spray combustion of residual fuel oil. And the nanoparticles that we produce this way are still used in inks, but also in tires and paints. And these nanoparticles are actually used even in novel energy applications, including fuel cells, batteries, and supercapacitors. Now, for the rest of my presentation, I will focus on the use of these combustion-generated carbonaceous nanoparticles for designing supercapacitors in particular. And for this reason, I will just give you briefly some context for this application so that you can better follow me. So supercapacitors have different properties compared to lithium-ion batteries. So unlike lithium-ion batteries that can provide us large energy densities, supercapacitors can actually provide us large power densities at very fast charge and discharge rates. So they are often used together with lithium-ion batteries in our smartphones and smartwatches to ensure their battery life. And also they are used in our computers to ensure the integrity of our data during power disruptions. Most importantly, though, I want to highlight over here that supercapacitors are included in applications that require large power densities that should be delivered at very fast charge and discharge rates. And these applications include wind turbines, as well as electric and hybrid aircrafts, and even hydrogen-based aircrafts. So the most widely used and commercially available supercapacitor device is the so-called electric double-layer capacitor. So there we have two porous carbon electrodes that are separated by organic or water-based electrolytes, as well as a glass fiber separator. So during charging and discharging of this supercapacitor, the electrolyte ions are adsorbed or desorbed from the pores of these porous carbon electrodes. So these electrodes are designed based on porous activated carbons, and more recently using porous commercial carbon blacks, such as the ketchum black grade that you can see over here. The performance of these supercapacitors is typically assessed using cyclic voltammetry. For example, here we did such measurements for supercapacitors that are based on a commercial activated carbon. So in particular here on the y-axis you can see the current density that was measured as a function of the potential. And we did this measurement here for a scan rate of 5 millivolts per second. This rate essentially indicates how fast we changed the potential during our measurement. And these small rates are typically used for supercapacitors that are included in smartwatches and phones, because there we need to deliver power for a long period of time. So the ideal voltammogram that we expect for a very good supercapacitor is rectangular, because it indicates that charging and discharging are symmetrical, and we have an efficient absorption and release of the electrolyte ions from the carbon electrodes. And the voltammogram that we obtained for this activated carbon is actually very close to the ideal shape. And we actually did these measurements also for a commercial carbon black grade, the ketchum black that I mentioned before. Here you can see that the voltammogram has also an ideal shape. However, its maximum current density is slightly smaller compared to that of the activated carbon. And this is due to the smaller specific surface area of this commercial carbon black compared to the activated carbon. So the current density depends on the porosity and the available surface for electrolyte ion adsorption and desorption. Now, we also did cyclic voltammetry measurements at large scan rates of, for example, 200 millivolts per second, that are essential for applications of supercapacitors in wind turbines, electric and hybrid cars, as well as in hydrogen-based aircrafts. So here you can see that the cyclic voltammogram that we obtained using this commercial activated carbon, as well as using this commercial carbon black, deviates significantly from the ideal rectangular shape. And this is due to the small pores that are present in these commercial porous carbons that limit the absorption of the electrolyte ions at large scan rates and reduce the current density. So by the end of my presentation today, I will show you how we can take advantage of the good understanding of carbonaceous nanoparticle dynamics that we have developed as a community for combustion synthesis of soot, and we can design this way supercapacitors that exhibit a superior performance, even at such large scan rates. In particular here, we oxidized a commercial carbon black using a thermogravimetric analyzer at the temperature of 1200 Celsius and an oxygen concentration of 10% of oxygen. So these conditions are present actually in the lean zone of this furnace reactor. These are the reactors typically used for carbon black synthesis. And of course, we are presenting the lean zone of aircraft combustors that I talked earlier on in my presentation. So at these conditions, you can see that the carbon black mass is actually reduced linearly as a function of the residence time, and the carbon black is completely consumed by oxidation within 30 minutes. Now, we collected about 40 milligrams of carbon black at 0, 25, 50, and 75% of conversion by oxidation. And we used these nanoparticles to characterize their porosity using different kinds of techniques. For example, over here, you can see a high-resolution microscope image that we obtained for as-prepared unoxidized carbon black. As you can see, these nanoparticles, we are talking now about single primary particles. These primary particles are not really porous. They have only a few tiny pores that are not really visible from this microscope image. But please compare this image to the one that we obtained after 25% of conversion. So at these conditions, you can see that oxidation starts to form small pores in the bulk, in the internal structure of these carbon black nanoparticles. And as the conversion increases to 50 and 75%, you can see that the oxidation results in the formation of larger pores and it disorders the internal structure of these carbon black nanoparticles. We have almost the formation of single graphene layers at 75% of conversion. Now, in order to better quantify the porosity of these carbonaceous materials, we did nitrogen absorption measurements. So here on the y-axis, I'm presenting you the normalized pore area concentration obtained as a function of the pore width. And in particular over here, you can see the pore size distribution that we obtained for as-prepared unoxidized carbon black. Again, you can see now more quantitatively that these particles contain only a few pores that are smaller than 2 nanometers. And due to the small porosity of these nanoparticles, their specific surface area is rather low. It's just 240 square meters per gram. It's much smaller compared to those of the commercial activated carbon and carbon black that I showed you earlier on. Now, at 25% of conversion, you can see over here that oxidation results in the formation of pores ranging between 2 to 4 nanometers. And this increases the specific surface area up to 680 square meters per gram. At 50% of conversion, oxidation results in the formation of several pores that are smaller than 2 nanometers. And at 75% of conversion, these pores start to fuse with each other and form larger pores in the range between 2 to 5 nanometers. And this further increases the specific surface area up to about 2200 square meters per gram. Now, I would like to highlight over here that the surface area, the large surface area that we obtained for these oxidized carbon blacks is mostly coming from the internal pores that are formed inside these carbon black nanoparticles. And to further elucidate this, I will present you next the normalized specific surface area on the y-axis obtained as a function of the carbon black conversion, that, as I showed you before. The specific surface area over here is normalized with respect to that obtained before oxidation starts. So you can see that at 75% of conversion, the specific surface area of carbon black is enhanced by oxidation by a factor of about 9. Now, we compared the measured specific surface areas to those predicted by the shrinking particle model that is commonly used to elucidate the evolution of the carbon black and soot particle size and surface area during surface oxidation alone. So you can see that this model underestimates the measured specific surface area up to 85%. And this is because it neglects the internal oxidation of these carbon black nanoparticles. So in order to assist the design of these porous carbon black grates, we actually developed a lattice Monte Carlo model to describe the evolution of the carbon black porosity during internal and surface oxidation. So we discretize this carbon black nanoparticle into a cubic lattice that has a cell size of 0.3 nanometers, and it contains in total more than 110,000 cells. And we elucidate the oxidation of this carbon black nanoparticle at the oxygen and temperature conditions that I showed you before. So at these conditions, oxygen diffuses throughout the carbon black nanoparticle. So we estimate the carbon black mass that is removed by internal and surface oxidation using this differential equation that we recently derived for a moving sectional model that describes the dynamics of internal and surface oxidation. So this differential equation gives the evolution of the particle mass as a function of the specific oxidation rate, omega, the external surface area, which is determined by the particle diameter, and the internal surface area, which depends on the internal pore structure. So here we had to make some assumptions. For simplicity, we firstly assumed that this particle contained only a single cylindrical pore with a size of about 80 nanometers. So it started from one side of the particle and went all the way to the other side. But this is just a simplified pore network that we used over here just to elucidate the dynamics of the pore structure during internal oxidation. We also simulated, though, particles that contained more realistic fractal-like pore networks. We derived these networks using the classic diffusion-limited aggregation algorithm. For your information, the pore fractal dimension that has been measured for soot and carbon black nanoparticles ranges between 2.28 and 2.21. So the pore fractal dimension that we obtained over here by diffusion-limited aggregation over more than 50 pore networks is in good agreement with the measured pore fractal dimensions. And it shows that indeed the pore networks that we use over here are rather realistic. So we're going to compare this lattice Monte Carlo model to the data and the shrinking particle model that I showed you before. So firstly, we run these lattice Monte Carlo simulations for non-porous carbon black nanoparticles. As you can see, the evolution of the specific surface area that we obtained this way is in excellent agreement with the shrinking particle model, and this validates our lattice Monte Carlo simulations. Now, here you can see the evolution of the specific surface area when we account for internal oxidation of a single cylindrical pore. So during internal oxidation, you can see that the cylindrical pore diameter increases uniformly. And this increases slightly the specific surface area at large conversions. But you can see that we still underestimate significantly the measured specific surface area. When we account, though, for the internal oxidation of more realistic fractal pore networks, you can see that the specific surface area increases up to a factor of 10 at large conversions. The shaded area over here quantifies the variability of the statistical variability of our model between the 50 pore networks that we used over here. So this model, this lattice Monte Carlo model for internal and surface oxidation of particles containing fractal-like pore networks can describe very accurately the specific surface area evolution of carbon black during internal and surface oxidation. And before moving on, I would like to mention over here that this model has been validated also with experimental data of diesel soot oxidation at low temperatures, which is relevant for oxidation of soot nanoparticles in diesel particulate filters. If you want to learn more about this, you can check our recent publication in Carbon. Now, at the last part of this presentation, I would like you to focus on the highly porous carbon black nanoparticles that we produced at 75% of conversion. The specific surface area of these nanoparticles is actually larger than the the largest specific surface area of the commercial carbon black grades that are currently available in the market, and it is on par with that of the commercial activated carbon that we used over here. Most importantly, please notice that the commercial activated carbon and carbon black that we used over here contain mostly pores that are smaller than 2 nanometers. In contrast, the highly porous carbon black nanoparticles that we produced over here contain pores that range between 2 to 5 nanometers. And this is quite important because this pore size range is ideal for supercapacitors used in hybrid electric cars, hydrogen-based aircrafts, and in wind turbines. And to further prove this, we actually did cyclic voltammetry measurements at the conditions that I showed you before, so at 200 millivolts per second, using this time the oxidized carbon black that we produced here. So the cyclic voltammogram that we obtained using this oxidized carbon black retains its rectangular shape even at these large scan rates that are relevant for wind turbines, hydrogen-based aircrafts, hybrid and electric cars. Furthermore, you may notice over here that the maximum current density that we obtained for this supercapacitor that is based on this oxidized carbon black is 60 and 160% larger than those obtained from a commercial activated carbon and the commercial carbon black. So good control of the oxidation dynamics of carbon black is essential to enhance its porosity and improve its performance in supercapacitors used in these applications. And with this, I would just like to go quickly to the summary of my presentation today. So again, carbonaceous nanoparticles have been viewed as a nuisance traditionally by combustion science and engineering, as soot is a major global warming pollutant and it is very toxic for public health. However, we still have large uncertainties regarding the climate and health effects of these nanoparticles. To this end, we developed a discrete element model that describes the evolution of the soot morphology during combustion. We validated this model with plenty of experimental data, and we coupled the simulated soot agglomerates that we obtained using this discrete element model with a global climate model to derive the direct climate impact of soot. So that way we showed that accounting for the realistic agglomerate structure of soot increases globally the direct radiative forcing of soot by 25 to 50%, and it explains nicely satellite observations. Most importantly, this model showed that at the hotspots of China, India, the Arabian Peninsula, and Western Sub-Saharan Africa, soot nanoparticles can increase the temperature by 0.75 to 1.25 degrees. Now, in addition to models, we also need novel flame reactors in order to characterize accurately the indirect climate impact as well as the health effects of soot emissions. For this, we used a flame reactor for enclosed spray combustion of jet fuel in order to produce large mass concentrations of aircraft-like soot nanoparticles. In particular, the soot nanoparticles that were generated using this flame reactor had similar physicochemical properties with those produced, with those measured for soot nanoparticles emitted from real aircraft engines. And the large mass concentrations that we obtained using this flame reactor helped us to characterize more carefully the health effects of these aircraft-like soot nanoparticles. Furthermore, using this flame reactor, we are able to elucidate the oxidation dynamics of soot in the lean zone of aircraft combustors. For example, we showed that we can practically eliminate soot emissions in the lean zone of this flame reactor by a judicious air injection. So next, we plan to use this novel flame reactor to investigate the dynamics of soot nanoparticles during combustion of novel sustainable fuels. And that way, we will be able to characterize more accurately their climate and health effects, as well as their oxidation kinetics that are essential to eliminate them from the atmosphere. At the end, the good understanding that we have developed for soot dynamics during combustion will contribute decisively to the design of functional nanomaterials for energy storage applications. For example, today I showed you that good control of the oxidation conditions of carbon black is essential in order to make highly porous carbonaceous nanoparticles that have a superior performance in supercapacitors used in wind turbines, hybrid and electric cars, as well as in hydrogen-based aircrafts. With this, I would like to thank you so much for listening, and I will be very happy to answer all your questions.
Thank you very much, George, for this